So coming, Happy New Year to everyone and welcome to this afternoon's session of the workshop. Before we start, there's a quick announcement that from tomorrow we are going to revert again to the original timings of the workshop, which means that we have a session in the morning, and that means that the bus from IISc is going to leave at 9:15 in the morning. So please keep that in mind. Okay, so the speaker for this afternoon is Kedar Damle from the Tata Institute of Fundamental Research in Bombay, and he's going to tell us about melting of three-sublattice order.
Thank you. So I'd like to begin, of course, by thanking Shubhru and others for the opportunity to come here. And I'm going to talk about, I think it's on. I'm going to talk about melting of three-sublattice order in certain easy axis frustrated antiferromagnets. And since I had imagined there may be a slightly broader audience here than the usual condensed matter seminar audience, I have sort of an initial part which is supposed to explain all the words I'm using, and then I'll come to the actual work. So for the experts in the audience who know the initial part only too well, it's a time you can check email or something. So let me begin with this initial part. So let me recap by saying a few things which we say in an introductory condensed matter theory course or solid state physics course. We start by teaching band theory, and we say if band theory works, you can think of electrons in a crystal as waves. They occupy modes which are set by the nature of the electrostatic potential of the nuclear array. But if you, on the other hand, have strong electron-electron interactions, this wave picture doesn't work so well, and it's much better to think in a slightly sort of dual way in terms of particles, and then you just think of particles that repel each other electrostatically and would like to be as far away from each other as possible. And the way that works then is that the electrons localize on individual ions, and they pay a large energy cost to hop to neighboring ions, and that's what we call a Mott insulator. And so the charge gets frozen in this Mott insulating phase, unlike in a band metal, but the spin of the electron remains a dynamical degree of freedom. So that's the starting point. We're talking about Mott insulators like this that can have intrinsic low energy spin physics, but the charge is frozen. So when I say the charge is frozen, this is of course a quantum mechanical statement. That doesn't mean that the electrons sit exactly still. There are virtual processes that are sometimes allowed. If there are neighboring ions on which there's an electron with an up spin and a down spin, then this electron can hop. This is a virtual process, and then come back without having to pay Coulomb energy. So this is just describing second order perturbation theory for the ground state. And this process is allowed. This one is not because of Pauli exclusion principle if there's exactly one orbital at each ion. And that means that the lowering of the ground state energy is sensitive to the pattern of spins relative to each other. This state will lower the energy relative to that state. And that's the origin of the spin exchange interaction between these localized moments in Mott insulators. It will generically lead in the simplest cases to an energy function that looks something like this, where the spins at neighboring sites interact via an antiferromagnetic exchange coupling. J bigger than 0 is what we call antiferromagnetic, because things like to anti-align to lower the energy. If you think of these as unit vectors and think of this as a classical energy. But you know, whether J is really positive, our nearest neighbor interaction is really dominant, these are quite difficult quantum chemistry questions that need calculations that go well beyond some simple second order calculation like this in some toy model. And they're really chemistry questions. And there are thumb rule answers to these chemistry questions, which I don't know too much about, I'm just mentioning them. But even beyond that, there are complications. The complications have to do with the fact that the Hamiltonian for the spins doesn't have to have full SU2 symmetry in spin space. Spin need not be conserved, that's because there's spin orbit coupling, as we know. So spin orbit coupling can make the Hamiltonian for the spins more complicated. There can be orbital degeneracies. In this cartoon I was drawing, there was just a single orbital at each ion that was active, But there can be many orbitals, and you can the electron can hop from one orbital to another on the same side. These are orbital fluctuations that can affect the nature of the spin Hamiltonian. And this can lead to a lot of very rich physics. That's the general setting. If you don't have all those complications and you just have a material where there's a bipartite lattice of magnetic ions with spins localized on them, and nearest neighbor antiferromagnetic exchange coupling J, then what happens at low enough temperature in 2 and higher dimensions, well, in 3 and higher dimensions at low enough temperature and 0 temperature in 2 dimensions, is that the spins spontaneously pick an axis in spin space and line up either along it or opposite it. So in a bipartite lattice, you have two sublattices. One sublattice of spins lines up along n, the other lines up in the opposite direction. So there's no net moment, but there's long range order. And there's spin waves which are gapless because you've broken a continuous symmetry. So that's Neel order, or antiferromagnetic long range order, which is the simplest thing that can happen at low temperature. But if you have a lattice in which these spins talk to each other via connections that don't make a bipartite lattice, if there are triangular motifs in the nearest neighbor connectivity matrix of your lattice, then if you insist on making some sort of a Neel ordered state, you get into trouble, because if you pick spontaneously an axis n, and if this spin lines up along the axis, and that one lines up against it, because you want to make this bond happy, then this spin doesn't know what to do. And this basic idea that because of the geometry of the lattice causing competition between various exchange couplings, the fact that these competitions don't allow you to realize the global ground state of the energy function, that goes under the name of geometric frustration. And this frustration is responsible for a lot of interesting physics, in some sense because it quenches the effects of the leading exchange J. If the leading exchange energy J picks a state, then that's all there is to it. But if there's this kind of competition and the leading exchange energy can't decide what happens at low temperature, then all sorts of other things can happen. It opens the door for a variety of normal low temperature states, and that's kind of part of the interest in this subject of geometrically frustrated magnetism. That is Mott insulators with spins living on lattices where the dominant exchange couplings compete with each other. So that's sort of the background. And there are many materials which have interesting low temperature properties that fall broadly in this kind of description, within this kind of description. The actual materials and their physics is not particularly important for this talk. I'm just putting this slide up to show examples of lattices. So for example, this is a lattice made up of corner sharing tetrahedra, which are regular and span space. And this is called a pyrochlore lattice. And it's an important example of geometric frustration in three-dimensional materials. There are layered materials where you have layers of the two-dimensional version of this, where you have corner sharing triangles that fill up a plane. Yeah. Yeah, there is some mineral which there are reports, it's not very well studied, but it's an insulator and it's supposed to have some strange low temperature physics. This is the notional formula. There's some old PRBs from the 80s, but it doesn't seem to have been, it goes under this name. It's some mineral that has been studied a few times, but there isn't much work. I think so. Yeah, otherwise it doesn't make sense. Yeah. It's surprisingly little work on this material actually, but there are a few papers before this became very fashionable, I think, mainly by people who just made the crystal or something. So there are examples where you have these corner sharing arrays of, regular corner sharing arrays of triangles that fill up the plane. And there are several examples of that. And there's of course the regular triangular lattice, which is a standard two-dimensional Bravais lattice, which is edge sharing triangles. Sorry. one of the complications I mentioned, which is spin-orbit coupling, sometimes that can be more than a complication, that can be the dominant effect, in the sense that the largest term in the Hamiltonian, the largest energy that the spins feel, can be an anisotropy term that likes the spins to point in a certain direction because of spin-orbit coupling effects. For example, you can have a term like this, which picks out an easy axis n, so that the spins like to line up along that axis n. And of course, this axis n has something to do with the crystal structure. So for example, in these pyrochlore materials of corner-sharing tetrahedra, these axes point outward from the center of each tetrahedron, and they're actually much, much bigger than the exchange coupling. And the exchange coupling is not even really nearest neighbor, it's more a dipole interaction that plays a role. So there can be situations where single ion anisotropy really dominates. There are two-dimensional examples where it's not so dramatic, but it still dominates. So it actually makes sense to study leading order, you kind of do an expansion and study the leading effects of J, starting with a Hamiltonian like this as your starting point. But that's not my focus today. I just wanted to mention that there are very natural examples where single anisotropy is very large. And the point of bringing this up is that anisotropy, especially if anisotropy that picks out a collinear easy axis, amplifies the effects of frustration. So for example, if you think of the level of a single triangle, although I said that the Neel state is frustrated, there's really no problem finding a unique minimum energy configuration up to rotations. You just pick a plane in which you put things at 120 degrees, and if you have an edge sharing arrangement of triangles, the triangular lattice, then this is the unique ordered ground state up to global rotations, and there's no really, subtle business having to do with ground state degeneracies if you don't have a easy axis. But if you had an easy axis, then you're back to the picture I was drawing earlier, and you really have a large degeneracy of inequivalent, symmetry unrelated, low energy states that are the best the system can do. So in this sense, anisotropy actually amplifies the effects of geometric frustration. Anisotropy that picks an easy axis certainly does that. And which then brings me sort of to the beginning of my talk at some level. So with that kind of motivation, you might want to study some simple model where you have this antiferromagnetic exchange coupling, which is dominated by a very large single ion anisotropy that picks out a certain axis, let's say the z-axis. If you think in some leading order approximation where you take just the leading effect of J, because D is much larger than J, then Sz will just be plus S or minus S at each site if these are spin S ions. And you can represent that by an Ising spin which is up and down, and you get essentially an Ising model with an antiferromagnetic coupling in front on a frustrated lattice like the triangular lattice. And this was studied way back by Wannier in 1950 as a simple example of what else could happen beyond Onsager's solution of the two-dimensional Ising model. And the interest in this is, of course, that if you ask what are the minimum energy configurations of this classical energy function, there isn't one, there's a macroscopic degeneracy. And this degeneracy can be captured simply by saying that in every triangle of the lattice, you want exactly one frustrated bond, one bond where the spins are aligned, not anti-aligned. And that, if you think about the dual lattice made up of centers of these triangles and links that are perpendicular to the sides of this triangle, becomes a dimer model on the honeycomb lattice. And that has a macroscopic degeneracy that has a non-zero entropy density at zero temperature, just for this simple classical model. And it's not clear what happens as you lower the temperature in this simple two-dimensional classical model. And in fact, that's what Wannier worked out partially, but the complete solution came a little bit later. So it was, I think, Stephenson's work that showed that if you calculate the spin-spin correlation function of this Ising model, you basically get a power law at zero temperature. And you take the t going to zero limit, even at zero temperature you have power law correlations, you don't have long range order. In fact, the power law has two components. There's a fast decaying uniform piece, and then there's an oscillatory power law which is 1 over root r. So this is the dominant behavior. And this is a remarkable, in modern fashionable language, this is a spin liquid state. The spins neither freeze. This is an exact Pfaffian calculation of Stephens. This is an exactly soluble model, right? Yeah. But it took a while, I think, before people figured out how to calculate correlation functions. I think Wannier's original solution didn't calculate correlation functions. That was done later. So this is the result for the correlation function on the lattice. Yeah. So, and he had, but there wasn't an explicit formula for the correlation function in the zero temperature limit. That was done, I think, quite a bit later. So this is a state in which you're neither a paramagnet with a finite correlation length and exponential correlations beyond that length, nor are you long range ordered. You have power laws like this. And so my focus is actually going to be easy access antiferromagnets of this kind on Kagome and triangular lattices. So here's another picture of these two lattices. They're going to figure largely in this talk, so I thought I'll draw them again. This is of course the standard triangular Bravais lattice, which you can represent with these two principal directions, these unit vectors at 120 degrees. And this you can think of as a triangular lattice of triangles. So instead of a side, you put a whole triangle down. So it's not a Bravais lattice, it's got a 3-point basis. Both have a natural tripartite structure. This has a tripartite structure of triangles, this has a tripartite structure for sides. Sorry, I didn't hear the question. Well, it's not bipartite because you can't split it into two groups of sides such that one talks only to the other, but you can split it in 3 groups of sides so that you never have connections within a group. So the neighbors of A are always B and C and so on, right? That's what one means by tripartite. Sorry? Okay, Senthil seems to have understood the question. Sorry, I didn't understand.
This is a Bravais lattice.
It's not bipartite, right? I mean, just think in terms of graphs. It's not even important that there's geometric lattice there. Just connectivity, right? Oh, wow. I think I'm going to make up for Gautam's marathon by ending early. Anyway. So, one thing I want you to notice is that, sorry, I'm going the wrong way. This oscillation is actually an oscillation at a wave vector that is commensurate with this tripartite structure of the triangular lattice. These are integer coordinates x and y along, sorry, how does this work? Along these two directions, ex and ey. So in that sense, you could say that in the zero temperature limit, the simple Ising model itself has power law 3-sublattice order. It is the correlations are such that they distinguish correlations within the A sublattice from correlations between A and B and A and C. And motivated by that, you can think in terms of an order parameter for 3-sublattice ordering on the triangular lattice. And the way you make the order parameter, of course, is you take the spin density and you just multiply it by the right wave vector, oscillatory function at the right wave vector, and sum up. So that's psi. And psi has a modulus and a phase which I call theta. And there are actually two kinds of, so in the Wannier solution or in the Stephenson calculation, there isn't long range order. But if that pattern actually became a long range ordered pattern, then there would be there are in principle 2 kinds of long range ordered patterns, both ordering at the same wave vector q, which in this notation of ex and ey will have components 2 pi by 3 and 2 pi by 3 in both those directions, right? So I should write that somewhere. So whenever I write q, so the two two kinds of phases you can understand in this way. So one of them, which I call the antiferromagnetically ordered three-sublattice ordering, antiferromagnetic three-sublattice ordered state, you first spontaneously pick one out of three lattices, three sublattices A, B, or C, and you decide that the spin on that sublattice is always going to be wildly fluctuating between up and down, so it's going to have no net polarization. So that I represent by a 0. So you spontaneously pick one out of three sublattices to do that. Now you've got two sublattices left. Then you spontaneously pick one out of the other two and polarize all the spins on that sublattice up, and then the remaining spins go down. So so that's the pattern I've drawn here. If you interpret the green dots as a 0, the red dots as a minus s, and the blue dots as a plus s. So you can see if I draw the spins out like this, you end up getting, I should draw this. You end up getting hexagons like this, which are up, down, up, down, up, down, and all talking to the central spin, which is 0, which is free to fluctuate because it has no net field, no net exchange field acting on it. The energy is not changed by letting the spin fluctuate, so it fluctuates wildly, and these are locked in this pattern. And now you can continue this pattern in the whole lattice, and that's one out of the 6 symmetry-related antiferromagnetic three-sublattice ordered states. You can also have ferrimagnetic three-sublattice ordered states, which you can understand by interpreting the colors slightly differently. Now you first decide spontaneously which sublattice out of the 3 is going to host a minority spin. So 2 sublattices are going to have spins that are going to be the same as each other. They're going to be the majority spins, and one sublattice is going to have a minority spin on it. So you spontaneously pick that sublattice. There's 3 ways of doing that. And then you put a spin down there, which is, let's say, minus s. And then on the other 2 sublattices, it will be plus s. Or you can do it the other way around. So that's why there are 6 states. And now what you get is, you get this 0 becomes a minus s, and these are all pointing in the same direction. And this is pointing down. And you can again continue this on the whole lattice. And both these patterns have the property that every triangle has exactly one frustrated bond, so the energy is as low as it can be. Yes? Yeah. No. So it's just fluctuating up and down. So I'm thinking on average. These are, if you wish, the expectation values of the spin in the ground state or in the low temperature to the Boltzmann weight. Quantum classical fluctuations, everything.
Suppose I just take a single spin.
Yes.
That's in a state that is never 0.
That's right. So 0 simply means it's on average 0 in terms of a time series. Yeah, sorry, yeah. So this is an Ising model. Yeah. No, so we've reduced the problem to things either pointing up along some axis or down, and if they fluctuate back and forth wildly as a function of time, you call that a 0, right? Now the fluctuation can be just thermal, or it can be actually quantum fluctuations, tunneling. Sorry. So I'll come to I'll come to that. Yes. So there's 2 kinds of 3 sublattice ordered states which have an order parameter given exactly by the same expression, and they differ from each other in the phase, in the argument of the complex number. This is a complex order parameter, and it has a phase theta, and theta takes on values 2 pi m by 6, where m goes from 0 to 5 integer. If you have ferrimagnetic 3 sublattice ordering, so one of these 6 states, and theta takes values 2m plus 1 pi by 6 in this cartoon if you have antiferromagnetic 3 sublattice ordering. So these are the 2 kinds of long range order patterns that are natural at this wave vector, which both have the property that every triangle has exactly one frustrated bond and the energy is as low as it can be. And the reason the system might want to select these is entropic, that there's much more entropy in the neighborhood of these states than elsewhere in this large low energy subspace. So there's a similar story on the Kagome lattice. So you can actually think about both these problems together because it's the same underlying Bravais lattice. The only slightly different additional ingredient is that now for every Bravais lattice site you have 3 physical sites and 3 spins. So you have to specify what happens at each of them. And the way this works again is very similar, except that there's a kind of an internal rotation here. So you can see the colors rotate anti-clockwise as you go along Ex and Ey, and clockwise if you go along the diagonal. And again, there's 2 kinds of 3-sublattice ordered states. There's ferrimagnetic ones, 6 of them, and antiferromagnetic, 6 of them. Again, distinguished by different values for the argument of the complex number, which is the order parameter. Yeah.
Triangular lattice for the Kagome lattice, the spin correlators are exponential.
So I'll come to that. Yeah. So there's no good motivation right now for considering this kind of ordering on the Kagome lattice. That's correct. What he's pointing out is that the same calculation, roughly speaking, that gave this result, if you work through the methods for the Kagome lattice, you would get an exponentially decaying correlation function in the 0 temperature limit. There's no tendency towards long range order of the pure Ising model. But I'm going to show you that there are very natural extensions which are very physical, which actually stabilize the same ordering on the Kagome lattice as well. On the triangular, you can easily believe that this power law order will get stabilized by the right perturbations because it's already there at a power law level even in the simple model. That's correct, yeah. So you can construct the order parameter in exactly the same way. You just also sum over the internal index alpha, which tells you which of these 3 states, basis states you're using, basis site you're using. So are there, for people who don't know this stuff, did this go by slowly enough that you know what I'm talking about? Because I want to talk about how this order parameter melts, how this ordering melts. So I want to convey what the ordering is before I talk about how it melts. Yeah, so that would be a slight diversion, but I'm happy to do that on the blackboard when I get through my transparencies. It's quite simple actually. So in this talk, I want to talk about how if you have low temperature, if you have a low temperature phase where there's long range order of this kind on the Kagome or the triangular lattice in some easy axis magnet, where there's a preferred axis along which the spins like to line up, then how does it melt as I heat it up? And I'll give you some background literature which explains how there are actually 2 well-known ways in which this ordering can melt, can go away. One is called conventionally 2-step melting, and it's 2-step simply because you go from long-range order to power law order at the same wave vector to a paramagnet. So that's the 2 steps. So that's one way this can happen. And the other way that's known in the literature is what's called 3-state parts criticality, where you lose this 3-sublattice order parameter, this ordering via a transition that's in the universality class of the 3-state parts model in 2 dimensions. So these are the 2 well-known ways in which this is known to proceed. And what I want to explain to you or convince you about is that, well, it's 2 things. One is that there's a very nice and simple thermodynamic signature. By thermodynamic, I mean you apply some field on the bulk material and you measure some response, which is like a susceptibility. You don't look more closely and you don't do scattering experiments of any kind. So there's a simple thermodynamic signature of this 2-step melting, which basically says that the susceptibility to an external field along the EZ axis, the uniform susceptibility to a uniform external field along the EZ axis diverges as a power law as you make B small, and you can predict what that power will be. It falls in this range between 2/3 and 0, and it's continuously varying in this power law ordered regime. So the idea is, if it's 2-step melting, your phase diagram will have 2 transitions like this. So here you will have long range order. Then you will go through a first transition where you will develop power law order. and then that power law order will go away at a second temperature and you will have a paramagnet. And in this entire region, you have uniform susceptibility to a field along the easy axis diverging as this power, which varies from 2/3 at the lower end to 0 at the upper end. Yeah. By power law order, I mean exactly what we found in Stephenson's case, like this. By power law order, I simply mean that there will be a cosine at the right wave vector, and then multiplying it will be a decaying function, which is a power. Now, it may not be 1 over root r, it will be 1 over r to some power. Yes, in the renormalization group way of thinking, in fact, it is. The power is going to be a function of temperature. In fact, that's well understood. I'll review that. Sorry? Long range order means at long distances you go into a pattern. Just leave out this 1 over root r. That's long range order, right? It doesn't decay. Yeah. All right. So that's going to be one statement, and the other is that there could be a generic way in which you could go from this two-step melting kind of picture to this three-state Potts criticality as a function of some microscopic tuning parameter via a multi-critical point M, which doesn't seem to have been studied earlier in the literature, and which I hope to convince you is an interesting point, about which there are some field theoretic questions, at least I have. So that's why I'm here, I guess, in this workshop. So those are the two main messages, and I will also leave you with some speculation that M might be accessible in what people call artificial Kagome-ice. I'll explain this in a minute. So it's in the universality class of the three-state Potts transition. That the process by which you lose three-sublattice order, that transition is in the universality class of the three-state Potts transition. Yeah, I think one can say it's between, yes. It's lower than 3/2, I think it's bigger than 1, yeah. I'll give you the argument, yeah. And so this is what I was saying earlier in words, which is that already the simple Ising model you can view as being characterized by incipient power law correlations at that wave. So incipient long range order at this wave vector, and some perturbations can stabilize this order. And the first example in the literature where some additional terms in the Hamiltonian were considered that stabilize this long range order goes back actually to very ancient stuff. And the motivation for this large body of work was systems in which you adsorb noble gas atoms on graphite layers. And the idea is that graphite has this honeycomb structure on the surface. I mean, kind of like multi-layer graphene, I guess. And your noble gas atoms are these big balls that kind of sit with their centers on the graphite hexagons. So the sites of our toy model, of our effective lattice model, are actually the centers of the graphite hexagons. And you must remember that these spins, this is just a simple lattice gas way of talking about some monolayer of noble gas atoms on the graphite substrate. And that's the context in which there was a lot of work done on models like this, where you start with the triangular lattice Ising model and you add some further neighbor couplings, typically a ferromagnetic second neighbor coupling and a third neighbor coupling and so on, and a magnetic field term to model this system. And when you add a ferromagnetic second neighbor coupling, immediately converts this power law three-sublattice order into long range order at the same wave vector. And there's a lot of Monte Carlo work from the 80s about this. One simple example where this kind of order appears and is supposedly relevant at least to some class of experimental systems. Now those experimental systems in magnetic language are always at non-zero magnetic field, because these noble gas atoms are so big, these circles are so big, that it's very hard for the system to get near half filling. It's very hard for the system to occupy half the graphite hexagons, which would correspond to zero magnetic field. So typically they are well away from half filling, so things I'm saying here which are close to zero magnetic field are not directly relevant, But this did not stop people from studying models like this at b equal to 0 as well. And that's the part I'm interested in. Another example where this kind of long-range order has appeared in the literature is more a theoretical prototype for the effects of quantum mechanics in frustrated spin models. And so, there was a quite influential paper written some 15 years ago, which talked about Ising models of quantum frustration. And their idea was that, it's a very difficult problem to think about quantum mechanical spins interacting with antiferromagnetic exchange couplings on non-bipartite lattices. And you can simplify it quite a bit by thinking of Ising models where you retain some of those features, you retain this frustration, but then the quantum mechanics is put in a very simple way. You just put in some transverse field that flips these spins, causes quantum fluctuations between up and down. So if you take the Ising model on the triangular lattice and add this transverse field term, it immediately again stabilizes in the ground state, long range 3-sublattice order. But this time the long range order is of the antiferro type. I should have mentioned that here the long range order that's stabilized is ferrimagnetic, which is this minus S plus S plus S kind of order. Here it's antiferromagnetic. And there's some intuition behind it. The idea is that quantum fluctuations, zero means it's actually polarized along the X. It's just quantum mechanically fluctuating between up and down. And that's the intuition behind preferring antiferro order. You want to create as many spins as possible that are flippable, that can take advantage of this transverse field and lower their energy, and that's kind of why this happens. Another example where this crops up is something Senthil and I looked at some years ago, where we were looking at models like this, which are spin 1 antiferromagnets with SU2 symmetry, but with a easy axis anisotropy that's reasonably strong. And then if you map if you ask what's the low energy physics of this and derive an effective Hamiltonian, it ends up being a model of hardcore bosons with nearest neighbor repulsion at half filling and unfrustrated hopping on the triangular lattice. And such models are known from Monte Carlo work again to have 3-sublattice ordering at low temperature in the ground state. And it's a bit confusing what kind of 3-sublattice ordering they have, because if you take this idea seriously that quantum mechanics likes to have as many flippable spins as possible, you might again postulate that you have this antiferro 3-sublattice ordering, but that doesn't quite happen. If you actually look at the Monte Carlo data, you see very clearly that the phase peaks at 0, 2 pi by 6 and so on. And so it's actually this ferrimagnetic 3-sublattice ordering that's favored. More recently, 3-sublattice ordering has cropped up in the discussions of what's called artificial Kagome-ice. And these are actually not magnetic compounds at all. They are artificially constructed networks of magnetic wires. So you take some magnetic material and make some very thin wire, and you construct essentially a honeycomb net like this, where these are now short segments of magnetic wires. And you can, subject to some questions about thermalizations, view each of these wires as a spin that's interacting with the other spins. And what you end up getting is a Kagome lattice system like that, where the magnetic moments live here, the dipoles live there, right? And there's been a lot of work, there's been many experiments that construct this and try to equilibrate it, because these are artificial things, they're pretty big. It's not so clear they actually go into thermal equilibrium. But subject to those worries, there's been a lot of theoretical work as well, trying to model the physics of these using simple Ising models like this. Here, these Ising spins have a slightly different meaning, because the easy axis are not collinear anymore, they're along the wire. But that doesn't change the low energy Hamiltonian, it just changes the interpretation of some results. And again, so the simplest model you can make for these wire networks, these artificial Kagome-ice systems, is you add further neighbor ferromagnetic couplings to a nearest neighbor antiferromagnet on the Kagome lattice. Yeah.
This artificial wire is not short range interaction.
Yeah, so actually So I'll just, exactly. So part of the experiment, part of the theoretical work assumed that you can truncate the dipolar couplings at, let's say, the second or third or fourth neighbor. But then there were more serious calculations done keeping the full dipole structure. And you actually get different results, not for the ground state. The low temperature state remains ferrimagnetically three-sublattice ordered, but the way it melts changes, depending on whether you take the full dipolar coupling or you truncate it. That's exactly right. In fact, yeah. So, yeah, I'll come to that, I think. So, if I want to talk about the melting of various realizations of this three-sublattice order, I should think in terms of this order parameter. And in general, one writes down some free energy functional for the order parameter, which is some polynomial in O. And if you neglect spatial variations as well as fluctuations, we all know that the phase transition then amounts to a change in the character of the minimum of this polynomial. That's Landau-theory. If you go in for a complete description where you include gradient terms as well, all possible symmetry allowed gradient terms, and integrate over field configurations, you can correct the mean field exponents, but typically you don't change the nature of the transition. You just change the detailed properties of the transition. And so in that sense, symmetries are usually decisive because they determine what terms you're allowed to write down. So in this case, if I apply that philosophy, I would write down Landau free energy in terms of psi, which has some modulus of gradient psi square, r mod psi square, this term. And then this would be the leading anisotropy that tells me about three-sublattice ordering and the lattice I'm on and all those details. So this is an allowed term at zero magnetic field, which respects both all the transformations of psi under lattice symmetries and the spin inversion that's a symmetry at zero magnetic field. And you could write down a lattice version of this, for example, if you don't like this sort of continuum theories. You could just take some coarse-grained lattice on which you have some phase-only model where you only worry about the angle, which is the argument of this complex number psi, and you write down some xy model for it with ferromagnetic coupling and this six-fold anisotropy term. And you can in principle write down other couplings as well which are consistent with the symmetries. You don't have to write cosine theta I minus theta j. You can write 2 theta I minus 2 theta j and 3 theta I minus 3 theta j. They are all allowed, and so you have this 3 or 4 dimensional space which is your effective model. And exactly this effective model or a version of it was studied many years ago by Cardi, where he didn't allow this angle to take all possible values from the circle. He made this term effectively infinite, so he restricted theta to take on 6 values, but then he wrote all possible couplings of this kind. Like I said, you can have theta I minus theta j, 2 theta I minus 2 theta j, or 3 theta I minus 3 theta j. And he analyzed the full phase diagram of this 2-dimensional stat-mech model using a bunch of duality arguments. And he realized that there's 3 generic possibilities for the melting, which are of relevance to us. One is this 2-step melting, which I talked to you about. The other is this 3-state parts transition. But now let me give you a little more detail. The way this 3-state parts works is, roughly speaking, there's an initial transition. So this is now so instead of that scenario, you can have a situation where you have a low temperature phase where e to the I theta is ordered. Then there's a 3-state Potts transition at which you lose this long range order, but e to the 3I theta still remains ordered. And then there is a second transition which is just an Ising transition at which you lose long range order in this field. So that's the full sequence that's possible. That's the other scenario that Cardi found. He actually found that you can also have examples where you invert the sequence of temperatures here. So you first have an Ising transition, and the intermediate phase is then characterized by a non-zero expectation value not of e to the 3I theta, but of e to the 2I theta. Basically, you are factorizing this 6-state clock model in 2 different ways, into 3 and 2, into an Ising and a Potts.
But in this scenario, the 50 points are related by relevant ordering, not an exactly.
So this is a long range ordered phase. This is not power law. So it's completely different. Although in both cases there are two special temperatures, the meaning is quite different. Here you have a second order transition in the three-state Potts universality class where you lose three-sublattice ordering. But this order parameter survives, and if you ask what this order parameter is, and I'll come to that more physically, it's actually net ferromagnetic moment. So there's a net ferromagnetic moment that's associated with this long range order that survives. And then this Ising transition is just regular loss of ferromagnetism. That's the. I'll show you in a second. So it's not obvious the way I was writing it, and that's part of the point. And I should mention, of course, that in his four-dimensional phase diagram, there's large regions where there's just a first order transition where you lose three-sublattice order and you just get paramagnet. That's always possible. And the way you understand that's always possible is you realize that if you fine-tune the values of these K1, K2, K3, you can arrange for this to have enhanced symmetry. Instead of 6-state clock, you can make it have 6-state pot symmetry, and that's certainly a first order transition. And then around it, there's a whole first order surface. So that's roughly how his argument goes. So that's always possible. Or you can have that, or you can have that. Or like I said, you can invert this, but that's not particularly relevant in any of the examples I'm talking about. It's not physically very well motivated for us. He was only talking about these clock models, not about the underlying magnetic system. So we can ask how this ordering melts in various examples that I listed. So in the transverse field Ising case on the triangular lattice, it's two-step melting, it's like that. In the ferrimagnetic three-sublattice ordering of these classical lattice-gas models is again two-step melting. And this is the part I was saying earlier. In the Kagome models I was talking about, it actually matters whether you truncate the dipolar coupling or not. If you truncate it at some second or third neighbor level, you get two-step melting. But if you take the full long-range dipolar coupling, including the tails, you actually get this other behavior. You get this three-state Potts transition. So it's sensitive. Yes, so this is quantum and this rest are classical. I can give you another quantum example because we looked at that. There was some argument, well, I was part of the argument. Prokofiev explained to me how I was completely confused about domain walls and how it would be a three-state Potts transition in this triangular lattice supersolid. So we looked at that. And you know, both are generic possibilities, it's hard to get it right. So you have to just look. And this is another quantum example where it's power law order in the middle. So we have detailed data now that shows that you go, so forget this black, it's just the loss of superfluidity, which is relevant for what I'm talking about here. The three-sublattice order goes in a two-step way with power law. Yeah, so this is this mapping that I was talking about. Sorry, go a little bit back here. So if you start with this model, which is spin 1 on the triangular lattice, the low energy effective theory is hardcore bosons, where, okay, so this is a nearest neighbor repulsion, which I'm calling V in that slide. So as a function of the nearest neighbor repulsion, you have a transition in this model where you develop three-sublattice order, and we are talking about how that melts. And so the melting is again a two-step melting. So in fact, the only example in the literature where you have this scenario, which is one of the possibilities Cardi describes, is here. So if you take the Kagome lattice model with full long-range dipolar couplings. So I already showed that. So this now brings me to the first punchline. So if you wanted to detect whether it's like this or like that, you would need a good way of detecting power law order. And of course, people do that, but they need to do some work. They need to do a scattering experiment in which you will detect some power law versions of Bragg peaks, or you will do some real space imaging, get lots of data and lots of image processing to decide that it's power law. And both of these are not totally straightforward things to do. And the point I want to make is that there's a very simple signature actually, which is a purely thermodynamic signature. Just put a field along the EC axis and you get a singular susceptibility in the power law ordered phase. And let me just say where that comes from. So you can predict what the power of this susceptibility is in terms of the power of the power law ordered phase, which I call eta. So this is actually a very simple argument, and the argument is like this. So in the power law ordered phase, a good description of the system is that this six-fold anisotropy term is irrelevant. In the long range ordered phase, it's relevant and theta locks either into that or that and gives you long range ordered state. Whether it chooses this or this depends on the sign of lambda 6. But in the power law ordered phase, lambda 6 is irrelevant. But you're not at high enough temperature that vortices in theta are relevant. So you're in this intermediate regime where neither vorticity nor anisotropy are relevant. And you then have a Gaussian free energy density at the fixed point with a continuously varying coefficient there, which can vary. So if you ask what are the allowed values of G, so that for vorticity is also irrelevant and six-fold anisotropy is also irrelevant. The six-fold anisotropy being irrelevant tells you that G must be bigger than 1/9. And as usual, the statement that vorticity is irrelevant tells you that G must be less than 1/4. So there's this range, which is a fixed line, which is what he was saying, where both vorticity and lambda 6 cos 6 theta are irrelevant. And the long wavelength description is just this Gaussian theory for the phase of the order parameter. And that's describing this power law ordered phase. So eta, which is this power of the order parameter fluctuations, the correlation function is just this G in the effective theory. Right? So this just goes back to the old work on KT transitions. So now here's my argument for the thermodynamic signature. Yeah. Yeah. Yes, yes, yes. So I forget about amplitude fluctuations. I imagine that modulus of psi is not critical. It's the phase that matters, right? And I'm writing down the theory just for the phase. Yes, and that's exactly right. Well, so I'm just saying this power law ordered phase, which I'm accessing as a function of temperature in this microscopic situation, is controlled by a fixed line, and that's the fixed line. So various points in this microscopic model at various temperatures, will flow under Rg to various G, various points along this fixed line, right? Yeah, yeah. So this is the fixed line that you claim would be the destination for the starting points that are here, right? So that's and you're just reasoning backwards. You're asking what are the values of G that would be consistent with this being irrelevant and vorticity being irrelevant. That's all. So now here's the point, and this also explains why this is three-state pots and what I mean by this. So one thing that's often overlooked in discussions of three-sublattice ordering, but which is very important for what I want to say, is that the Landau theory is actually not complete. Because there's another mode which is important and which talks to the order parameter, which we are leaving out. And that mode is the uniform magnetization mode M. Because there's a kind of allowed Landau theory coupling, which is M times real part of psi cubed. The only reason we left out real part of psi cubed was that it was odd under spin inversion, which is a symmetry if you have zero magnetic field. But M is also odd under spin inversion. And so this is a allowed term. And you must include it and ask what effects it has in various parts of the analysis. And it's formally irrelevant along the fixed line. It's formally irrelevant along this fixed line. And so the physics of two-step melting, the fact that you have this power law ordered phase, is unaffected. But it's dangerously irrelevant in the sense that not keeping it would let you miss some important physics. And the important physics you would miss is the power law correlations of M. So if you had this theory and you added to this a term which was M cos 3 theta, which is in effect what I'm doing when I write this, then M will inherit the power law correlations of cos 3 theta without changing any of the physics of this two-step melting. That's clear. I mean, it will lead to some renormalization in the value of G, but that's anyway some microscopic detail. It will lead to some change in what temperature maps to what value of G, but it won't change the long wavelength properties of this. What it will do is it will endow M, the uniform magnetization density, with power law which is 1 over R to the 9 eta, if eta is the power law for the order parameter field. And that's just because it's a Gaussian theory and I'm taking the third power, psi cubed. But this, remember, eta is varying between 1/9 and a quarter. So 9 eta is varying between 1 and 9/4. So for a large part of this power law ordered phase, in a large region, almost all the way up to the upper temperature T2, the corresponding susceptibility, the uniform susceptibility, which is just the integral of the correlation function, is divergent as a function of system size. If you're doing finite size susceptibility in a L by L box, that will have a regular part, but it will also have a part that will be L to the power 2 minus 9 eta, and 9 eta, so when 9 eta is less than 2, this is divergent. So the statement would be that in the thermodynamic limit at B equal to 0, the uniform susceptibility would diverge in the range 1/9 to 2/9, which means just slightly below T2. Because 2/9 is just slightly below a quarter. The cosine 3 theta is always relevant, but it's not cosine 3 theta that we are adding. We are adding some additional field tau if you want to think in terms of, so if you want to think in terms of lattice theory, you now have a theta and you have another Ising field tau, which is the direction of the uniform magnetization locally. And you're not adding cos 3 theta, you're adding tau cos 3 theta. And tau is fluctuating. So that's why it's irrelevant. So there's no doubt that it's irrelevant. I mean, it's m times real part of psi cube. So it's irrelevant, but it affects the correlations of m. In that sense, it's dangerously irrelevant, right? And so you get. So that's right. So the full power law ordered phase goes from 1/9 to 1/4. But this thermodynamic susceptibility diverging stops at 2/9, which is slightly below a quarter. So there's so there'll be some small bit here where the thermodynamic susceptibility doesn't diverge, just below T2. But for the rest of this, it's divergent. So I'm just so I guess I'm mixing up language here. So let's work in this language, right? So in fact, I think I have a slide where I work in consistent language. So let's come back to, hang on. Somewhere I have a, okay, never mind. So what one can do is one can take a lattice model, instead of writing it like that, one can start with a minus j xy. This represents the ordering tendency to three-sublattice ordering. We can add this represents the sixth order anisotropy. Then we can add a completely different part of the story, which is some Ising coupling for some Ising degree of freedom, some ferromagnetic Ising model for the taus. So these taus are supposed to be direct, so you break up the system into little clusters. The taus are the direction of the net magnetization of each cluster, right? And theta is the phase of the local order parameter, three-sublattice order parameter of each cluster. So that's the coarse-grained model you write down. And then you have a coupling between this and that, which is this. So that's the full, I'm claiming that just this, which is equivalent to the standard Landau theory, is incomplete, and a more complete description would include the ferromagnetic order parameter mode, the uniform magnetization mode, and write down a standard 5/4 theory for it in continuum language, or an Ising model for it, and then couple the two via this symmetry allowed term. That's all I'm saying, right? And so I'm now trying to understand the effect of this coupling, tau cos 3 theta, in the power law ordered phase controlled by this fixed line, right? So that's what I'm doing. And so that's why it's irrelevant, but it's dangerously irrelevant, and it gives you this result. So of course, this is just the result in zero magnetic field in a finite box. That's not what we are after. What we want to talk about is the B dependence in the thermodynamic limit. There's a natural way to go from one to the other. If you add a uniform magnetic field B, then you're allowed a term which is just cos 3 theta, not tau times cos 3 theta. Because now you're allowed psi cube plus psi star cubed as a allowed term, because you no longer have spin inverse as a symmetry. You've broken that by adding a magnetic field. So there's an additional term which is just H3 cos 3 theta that's allowed, which is strongly relevant throughout in this entire temperature range, and it's relevant with this Rg eigenvalue. And so it implies that there's some length scale which goes like this based on this Rg eigenvalue, beyond which the system will just have threefold symmetry breaking, like a three-state Potts model, right? And so if I want to know what happens in the thermodynamic limit at small fields, I just replace this box size L with this correlation length scale, and so I get this final result. So that was one out of my two advertised punchlines. And the other one, I think now is quite clear. So let me first show that this works. So we've done Monte Carlo simulations in pretty much all the examples I told you about to check that this really happens, and it does. So here I'm showing the order parameter susceptibility, which is roughly speaking the integral of the correlation function, that's the part that's oscillating as the three-sublattice wave vector. And here I'm actually plotting the physical uniform susceptibility. And I'm fitting this to a power law. This is log scale. So I'm fitting this to a power law using that exponent and then doing just with that exponent fixed. So I multiply the exponent I get here by 9 and use it to fit to this L to the 2 minus 9 eta, and that's the fits. So it works in the transverse field Ising model. It works in the ordered phase of that boson model which has a super solid phase. It works in a whole bunch of examples that we've looked at. And this is what I was talking about. This is exactly this. So you write down now a more complete coarse-grained description, which is an XY model with 6-fold anisotropy, an Ising model with a magnetic field, small magnetic field, that's the external field, and this coupling term, tau cos 3 theta. That's behind this description. And I should mention that this is not entirely obvious if you think microscopically, because here's a example where you have the triangular lattice Ising model with a transverse field. In the low temperature limit, it's antiferromagnetically ordered in the sense that one sublattice is pointing along the x direction, one sublattice is up, one sublattice is down. There's absolutely no net moment. And if you looked at the ferromagnetic susceptibility in the low temperature limit, in the ordered state, it's finite, it's small. But then you heat the system up, the ferromagnetic susceptibility diverges. So it's a kind of a counterintuitive result, but then when you think about it, it's not so hard to understand. So then I can think more carefully about the nature of the phase transitions that are possible. And in this language, actually, you can understand at least two of Cardy's scenarios very naturally, if I think like this. So let me explain that. So let's look at the dotted lines first. So I'm now drawing the schematic phase diagram of this effective model at fixed values of jxy and h6 and j theta tau at h equal to 0, varying j Ising. And in my mind, j Ising controls the ferromagnetic fluctuations, and it's actually the result of these further neighbor ferromagnetic couplings in the microscopic model that produce a tendency towards ferrimagnetism. So that's what's being modeled by writing this. So my idea is that if I, in this Kagome lattice model that people have looked at, if you change the strength of the further neighbor ferromagnetic coupling, what I'm tuning in this effective model is j Ising. Is the same as Landau-theory in that, yes. Sorry. Yeah, so I should have, yeah, so actually, yeah. So I should consistently refer to all terms like this as H and terms that couple as J. So that's why, yeah. So that was bad notation on the blackboard. So therefore it's kind of natural to hold everything else fixed and ask what happens to the nature of the melting as a function of j Ising for fixed values of everything else, right? Fixed order 1 values of everything else. So here I'm drawing first the phase transitions, the known phase transitions of the XY model with 6-fold anisotropy and the Ising model. So of course, the Ising model has a transition temperature that scales with J Ising, so that's this straight line. And the XY model has two transitions, T1 and T2, because it's 6-fold anisotropic. It's this clock model. So there's this theta1 and theta2, and there's power law order in the middle. So now what you can do is you can break up your analysis of the effects of this coupling. So you want to understand how this phase diagram changes when you couple the two theories. So you can break up your analysis in two parts. One part is when the Ising temperature is bigger than the XY temperatures. And then the Ising model orders ferromagnetically first, and because it's ordered ferromagnetically, it leads to basically a term which is a threefold field on the XY model, a term like cos 3 theta, right? Because in this theory, you can imagine this develops an expectation value, so you're just left with a cos 3 theta. So then it becomes like a 3-state Potts model. This is why it's 3-state Potts, the transition. And so then there's a higher transition which is Ising, followed by a lower transition which is 3-state Potts. And now you understand sort of more physically what is the meaning of 3I theta being ordered but I theta not being ordered. It's simply the statement that the Ising model is ordered, then there is net ferromagnetism, but there isn't net 3-sublattice order in this intermediate region. So this is the scenario, this is one of the two generic scenarios of Cardi. And on the other side, when the Ising temperature is lower, then all the Ising model does is it kind of bends the lower transition up, so that you have a pinch off of this power law ordered phase. And so you have this power law ordered phase that pinches off, and then on the other side you have these two. Now this is in the specific model I wrote down. I'm not sure that the right hand side of this phase diagram is as generic as the left hand side. So let me talk about that. But anyway, so this is the multi-critical point I'm talking about. Which is the interesting way in which you could go from this kind of melting to that kind of melting. Interesting generic way in which you could go from one to the other as you boost further neighbor ferromagnetic couplings in any microscopic situation. And so this, the phase diagram I displayed also explains why I say this. I should probably not have the equal to's there. The idea is that clearly there's, sitting at M, there's some relevant direction that takes me to the power law ordered phase. And that's a C equals 1 theory, so M must have a central charge bigger than 1. And likewise, if I take a decoupled Ising critical point and a XY critical point, the decoupled theory has C equals 3 halves, and but it would also have Gaussian fluctuations for theta. But then there's this relevant operator that couples the two theories and flows off to this M. So M must be less than 3 halves. So that's M is between 1 and, the central charge is between 1 and 3 halves. What it is, I don't know, unfortunately, because I have not measured it. What I have done, if it helps, is look numerically. So I discretized, I took this model seriously. I put it on the triangular lattice just to, just because it seemed kind of elegant to keep the lattice the same. But now it's a ferromagnetic model, there's no mystery about it. And you can do simple classical Monte Carlo simulations and locate this multi-critical point, which I did, and you can measure exponents. And so this is sort of the best data I could get. This is sitting at the multi-critical point, or at my best estimate of the multi-critical point, and here I'm plotting on log scale. So this is 600 by 600 systems, basically. Big classical simulations, easy to do. So I get pretty good power laws. Pretty reliable power law fits, and I'm monitoring the power law exponents of tau, which is the net ferromagnetic moment, the Ising field, e to the I theta, 2I theta, and 3I theta. By symmetry, of course, I expect 3I theta to have the same power law as tau, and sure enough, the red and the purple, I guess, have the same slope, and so e to the 3I theta and tau have anomalous exponent that my best estimate is that 0.20 roughly, and then the e to the I theta, the order parameter field is slightly bigger than Ising, looks like it outside the error bars of the Ising critical exponent, and 2I theta is this funny number, which is what tells you, which is I think the most important statement. because this is a number that tells you that you're completely non-Gaussian. Your fluctuations of theta are very far from being just what you would expect at the power law ordered way, right? You would have expected this number to be 4 times that number and this number to be 9 times that number. It's nowhere near that. So this is some, I have these numbers, I don't know what they mean. And that's why, yeah. Sorry? Measuring C. I think there's no problem as such. I was working in an effective, I was just doing classical simulations. I would need to do transfer matrices or do the equivalent quantum chain and then do DMRG or something and get the L dependence of, or the entanglement entropy, right? So since I was just doing straight Monte Carlo simulations of the classical problem, no reason why it can't be done. But you know, I just did this to begin with. I just wanted to convince myself that it's a non-trivial multi-critical point. It's not some simple thing where it remains Gaussian and pinches off. That can't happen anyway. But you know, this is concrete evidence. So that's this new multi-critical point, which is the second punchline I wanted to get to. And I'm only 10 minutes over time. And the speculation then is that, you know, if there are systems in which the relative strength of the second neighbor exchange, ferromagnetic exchange, is tunable relative to the nearest neighbor antiferromagnetic part, you can actually drive the system from power law ordered, power law melting, you know, two-step melting to the other kind of melting via this multi-critical point. For example, in these artificial Kagome-ice systems, clearly as I interpolate between the full dipolar interaction and the truncated one, I must have something in the middle which could be this multi-critical point. Of course, it could just be first order in the middle, nobody rules that out. And in fact, that brings me to my sort of questions or thoughts. And so let me stop here and then I can tell you what I'm confused about on this slide. So I'll come back to this slide, but first let me acknowledge students and ex-students and computational resources at TIFR. Thank you. So now I'll put up my confusions.
Questions?
Yeah, so it's in the right ballpark, I guess. There's a whole series of them. There's some supersymmetric series that ends at 3 halves. So it could be one. But so that's actually the last question. I mean, I don't know how to decide based on available data whether something is supersymmetric. What would I look for? Yeah, but is there some sort of yes/no question I can ask about some correlation functions being the same as some other correlation functions? So he's, I think, starting from the statement that if you have one Ising model which is C equals half and one boson which is C equals 1, then in principle that's one fermion and one boson, so it's supersymmetric. Yeah, that's one complex boson and one Majorana fermion. So no, but that is, so there's one, so the end point of this series is supposed to be 3 halves. Yeah. Something like that, I think. Gautam is the guy who told me about it, so we should ask Gautam. Yeah, the problem is yeah, that's right. Yeah. These are the only ones that are known, I guess, or a few of them. But anyway, let me first say some more basic things I'm confused about. See, I tried to sell this by saying that once you include the effects of the other field that people have left out of the analysis, you will end up with this phase diagram. That's not strictly true, because that just happens in the particular lattice realization of the effective model I wrote down. You can have many other things that happen. For example, let me just draw 2 or 3 possibilities. You can have this pinch off, so this is power law order, this is long range order, this is para. You can have this pinch off, and beyond the pinch off you can just have first order. Right, you can have this. You can also have a situation where you can have this pinch off, you can have first order, and then you can have this 3-state pots and Ising. And I think in the models Cardi looked at, these generalized 6-state clock models, something like this happens at least along some cuts, right? Because he has this large first order surface in the middle. You can have that. You can also have situations where the ground state just changes character and becomes a ferromagnet. It's kind of a degenerate case. You can have this, and then you can have this first order line, and then this is just Ising. And so this is just a ferromagnet. So there's a whole zoo of possibilities, right? And somehow it seems to me that it's not important which of these possibilities is realized on the right hand side. And the universal defining property of this multi-critical point is the fact that you have this power law region pinching off at a point. So you're going from eta equals 1/4 to eta equals 1/9 as you go down, and you're doing it faster and faster and faster and faster until this Gaussian theory becomes unviable and it's pinched off. And I think what happens on the other side is in some sense a statement about where the flows go to if you perturb from the multi-critical fixed point in that direction. But they don't change which multi-critical point you're sitting at. Somehow the defining property of the multi-critical point is this pinch off and not what happens on the right. That's somehow how but I've not been able to make this a sharp statement or think about it carefully. That's why I'm mentioning it. So anyway, so that's what I mean by saying, does M come in many flavors? Are these different points in terms of their long wavelength properties, or are they the same? These three scenarios I drew here. So because we've looked now at a bunch of microscopic examples, these Kagome lattice models on, it's very hard to do numerics in the vicinity of this multi-critical point. And at least in some examples, we find some impossibly small window which looks first order. So almost this scenario that I was drawing, the simplest one, but this really tiny region which could be a single first order transition and then this. And so the question is, if I approach from here in a microscopic realization like this and I get here, is it the same multi-critical point I'm talking about? So people have some ideas. So that's sort of my entry ticket into this workshop, these questions. Thank you.
So let's thank Kedar for the talk, and also Shubhrata for chairing the session. And, for the ISC participants, the transport back is as written on the board at 5, 5:35, 6:30, 7, 7:25, and 8:30. And for the NCBS people,